We got into kinetics last time. And remember, as we talked about, the study of kinetics really is the study of sort of the rates of reactions, how fast or how slow a reaction takes place. Um, and usually for reactions, a lot of times we look at rates as, something like this, molarity per second, molarity being the most common unit of concentration. And obviously, when we do experiments, we probably don't run them from days or weeks or years. So within minutes or seconds is a very common unit of time. So molarity per second is, again, typically how we see a reaction changing over a period of time. We talked about the rate expression, which is one way we could really sort of assess what is going on in a reaction. And again, in a rate expression, you have a reaction such as this, we could go that the rate is equal to 1 over A, and this would be negative because it is a reactant. So as we talked about, we should expect the amount of that or concentration of that to be decreasing with time, because obviously that is what we need to make our products. So it should be dropping down. That is what the negative there sign helps us sort of achieve, change in the concentration of A over the change in time. We also take 1 over the coefficient, as we talked about and did in a couple of examples, to take into account the mole-to-mole relationship of everybody. So we have the right sort of stoichiometry going on with our sort of kinetics information. We could also set that equal in this example here to our second reactant minus 1 over B, change in concentration of B over change in time. And we could set it to our product, which would be 1 over C, change the concentration of C over the change in time. Here it is not going to have a negative on the product side. Again, we should expect it to be increasing with time as that is being made. So we saw some graphs where we expect the reactants to sort of drop, products to sort of rise as this reaction sort of takes place as we go through it. That is because, again, when we do the change, for example, of something like A, its final concentration will be less than its initial. So when we do final minus initial, we will get a negative number, and that negative in front will turn our rate into a positive number, like we talked about, which is essentially what you want, is a positive number for the rate. We can tie them all together like we did here. We can kind of break them apart and use them individually, and it is really being able to figure out, something like the rate, average rate of the reaction, that allows you to figure out how everybody else is changing. So the value of the rate expression, as we talked about, is if you know pretty much how just one thing in that reaction is changing, you can pretty much figure out how everybody else sort of changes in accordance to that. We then talked about the rate law towards the end, and the rate law looks a little bit different. Is the rate, for example, k times a to the x and b to the y, if we were still using, say, this equation here. And one major difference between sort of the rate expression and the rate law is the rate law really only deals with reactants. So it's just reactants that are involved in the rate law. As we talked about last time, this little k, which is lowercase k, as we talked about, that is the rate constant. And again, that sort of gives you an idea as to how fast or slow the reaction is taking place. The x and the y here, as we talked about, these are what are referred to as the orders. And x would be the order with respect to A, and y would be the order with respect to B. You could get the overall order of a reaction by adding those together, x plus y, or however many you may have, and I'll give you your overall order in this particular reaction. Now, the orders and really the rate law is always found experimentally, and we're going to talk about it here in a second, but the roll sheet didn't get over there, making sure to sure how bypass the entire middle section, but all right. But the rate law is found experimentally, so as we will see, we are given pretty much experimental data that we need to use to help us calculate each of these things. The orders here are not, again, the coefficients that you see in the balanced equation. They could end up being the same number, but that's, again, not how we get those numbers. They do need to be found sort of experimentally. Now, one of the things that we saw, and I think what we finished up talking upon last time was the idea of these orders. And if you know the rate law for a particular reaction, you could use it to your advantage. You can, again, if you have a reactant that has maybe second order and one's first order, by playing with the concentration, a guy that has second order, you could really affect the reaction, either make it go faster, slow it down. You also can do it with somebody that has a smaller rate or order there, like 1. You could use it to adjust the concentration. We also saw that if you do have a order of 0, right, it does equal 1, which means that that reactant would not have any effect on the rate of the reaction. So you could do whatever you would want to that one. It would not speed it up or slow it down because it's not going to have any effect on that. Any questions on any of that stuff we talked about, I think, last time? God. All right, so let's talk about how we can determine really the orders of each reactant, how we can really determine the rate law, and ultimately as well, how we can determine the value of the rate constant. So this is a typical type of table that you would see for a reaction. And here we're looking at F2 plus ClO2. And this is typically what you'll see. There's multiple experiments done in this table. In this case, there's just 3, but there could be 4, 5, 6, as many experiments as you want. But in this case, there happens to just be 3 of them. And we typically will find in a table like this the concentrations of each of our reactants and really the initial rates that are sort of found through the experiment as well. And I would recommend that probably for most people, a more mathematical approach is probably the way to go when trying to determine the orders and stuff like that. So that's what we're going to talk about here. And we could use an equation or formula that sometimes looks like this. We could take rate 2 over rate 1 equals K A to the X, B to the Y. And obviously, if you had more reactants, you could add to it. And just generically A to the X and B to the Y. So what we are looking to do here is, I know it says rate 1 and rate 2. That does not necessarily mean that you go to the table and take like the first and second entry. What we're trying to do here is pick 2 entries in the table. And the idea here is to have pretty much just one unknown. And the way we're going to be able to achieve that is when we look at the table, we want to look for 2 entries where one of the reactants stay constant and the other one varies. That way we don't have too many unknowns at once. So for example, if we did look at this in this coincidence here, entry 1 and entry 2, the F2 remains constant, but this guy here varies in concentration. So we could use those 2 to help us figure out the order for the guy that basically is varying here. So if we write sort of the generic rate law here for this reaction, it would be the rate is equal to K times F2 to the X and ClO2 to the Y. So again, the goal here is to kind of figure out what everything is. So if we look at experiments 1 and 2 from the table, and again, that's going to keep our first guy constant and vary our second one. We're going to put all that information into this formula. I personally would recommend that you take the guy that has the higher rate and put it up on top. It gives you a little bit more whole numbers, a little nicer numbers to work with, but it really doesn't matter. You could go the other way. You'll just more often get a decimal rather than a whole number. So sometimes it's easier just to take the one that has the larger rate of the 2 and put all that information on top. So for my case here, it does look like the second entry has the larger rate. So everything from the second entry is going to go up on top. So I'm going to start with the rate, which is 4.8 times 10 to the minus 3, I think it says. Minus 3. It's going to equal K times the concentration of my first reactant, which in this case is 0.10 to the X. And my concentration of my second round, which is 0.04 to the Y. So everything that I put up here on top all came from the second entry in the table. Any questions on that there? I'm now going to put my first entry all across the bottom there. So go with everybody in this entry here and put it on bottom. So starting with the rate there, we got 1.2 times 10 to the minus 3 molar seconds. We have K, 0.1 to the X and 0.01 to the y here, right? And obviously these are polarities and all these. All right. So at this point, we're going to do some math. So when I divide out the left-hand side here, I hope that equals a 4. And now when I come to the other side, this K up on top, right? And this K on the bottom, that is the rate constant, right? And the rate constant is the same or a different number? It is the same, although we don't know what it is at this point, but it should be the same number for doing this, right? So I do know that that's going to cancel out. Now, since this is the same reaction, although we do not know what the order of X is at this point, we know it should be the same number. So that means that these guys are going to pretty much cancel out as well. That means that what we are left with when we divide out the other side is 4 to the y in this case. Yeah. Any questions on that there? Yeah. It's going to be the same number on top and bottom. The X on top and the X on the bottom should be the same. So the orders for all these reactants should be the same no matter what experiment you did, because it's the same experiment, same reactions, same conditions. Just like the rate constant should be the same because it's the same conditions on all those experiments that are there. So at this point, although we don't know what it is, we know it should be the same number, so it should cancel out. And that's why when we chose these two entries, we wanted those concentrations to be the same for that particular reactant so that everything would cancel out and we wouldn't have more than one unknown, right? All right, so at this point, you probably can visualize that y here would equal 1 in this case, yes? By the way, if you didn't have really pretty numbers like this, you could do a little natural log of both sides and divide, yes? So if you didn't have pretty numbers, or if you had pretty numbers and you don't know, you could take the natural log of both sides. When you do that, by the way, the y comes down. Then you could divide the natural log to both sides. And then you get the same answer. Or you could just look at it and get 1 in this case. So they won't always be maybe nice, pretty numbers, especially experiments that you do. They may not be really nice. A lot of times in books, they may be nice numbers, but or they may be very close to a whole number, which you can round. So, for example, if you had like a 3.99 or something like that, it's close enough to 4 to call it a 4 on that side. Any questions on that there? So what we just determined is the order with respect to ClO2 is first order. Now that we figured out the order with ClO2, what we want to do now is really go back to our tables and we want to find 2 more entries. But in this case, we actually want to vary the F2 concentration, but keep the ClO2 constant. So in this case, it looks like experiment 1 and experiment 3 will keep the ClO2 constant and it will vary our F2 in this case. So we're going to do basically the same calculation here. We're going to take experiment 1 and 3 in this case. And once again, I'm going to choose the larger rate to put on top just to give me more of a whole number. So for me, everything in experiment 3 is going to go up on top. So 2.4 times 10 to the minus 3 equals K. 0.2 to the X, 0.01 to the Y. Everything from experiment 1 will go on the bottom, 1.2 times 10 to the minus 3, K, 0.1 to the X, and 0.010 to the Y. So we're going to do our same sort of calculation here. We're going to divide out the left here, which should give us a 2. Once again, the rate constant should be the same on top and bottom, so as you cancel, we already calculated what this y is, and it is the same on top and bottom, so that again should cancel. That leaves us 2 to the x, which again, in this case, you could probably visualize that x would equal 1 in this case. Any questions on that there? So that x would be the order with respect to F2. That means that now that we have the actual orders of each of these reactants, we could write the completed rate law, and the completed rate law should look something like this. The rate is equal to K, F2, and ClO2. And much like most things in chemistry, if it is first or 1, you don't need to put the 1 up on top, so we don't typically write it. So if you don't see any number written on top next to the F2 or the ClO2 in this case, they're assumed to be first order for each of them, just like normal. That means the overall order of this reaction is actually 1 plus 1, which would be second order. So this particular reaction is second order overall. Any questions on that? So now that we took our experimental information, it allows us to calculate the orders. And once we have the orders and really the completed rate law, what we can do now is actually use our rate law to figure out what the value of the rate constant is for this particular reaction. So to figure out the value of the rate constant in this case, I'll take our rate law, which in this case is our rate is equal to K F2 ClO2. Solving for K means we're going to take all this and divide it over. So that would give us K is equal to the rate divided by F2 and divided by ClO2. So the question is, where can I get those numbers from? And the answer is I could get it from my table here. Doesn't matter which one I choose, experiment 1, experiment 2, experiment 3. It shouldn't, because it's a rate constant, which means no matter which experiment that you choose should give you the same number. You just can't mix and match, obviously. So you got to put everybody in there. So I'm just going to take everything from experiment 1 and toss it in. So when I do that, that will give me 1.2 times 10 to the minus 3 molar seconds divided by our F2, which is 0.1 molar, divided by 0.01 molar. Putting those guys in there will give me 1.2 to the minus 3 divided by 0.1 divided by 0.01. Going to give me a rate constant of 1.2. The units in this case are molarity on top, molarity on the bottom is going to cancel 1 over molar seconds. Yeah. Or sometimes people write it something like that as well. Yeah. So 1 over molar seconds is the units that is associated with this rate constant. And this is a second order reaction. As we will see as we go through this chapter, those are the typical units that you see for a second order reaction for the rate constant. So I think I might have mentioned it the other day, but very commonly when you get to certain problems, they will not tell you what the order of the reaction is, but they will give you the value of the rate constant. And if they give you a value like this and you see 1 over molar seconds, that should tell you that we're dealing with a second order reaction overall. And there's specific sort of formulas that you should use if it is sort of a second order reaction. Any questions on any of those steps there? So this is a mathematical approach, which again would probably recommend for everybody so you could show your work. Yeah. You can, if you understand, like you doubled the concentration, it doubled the thing. It's like a 1-to-1 type of thing and that type of thing. You could do that. But you do on an exam or quiz got to justify it. So if you choose not to do the mathematical approach, you do in words, need to sort of explain how you got to those orders. So I would highly recommend just doing the mathematical approach to it. Let's take a look at one here. So the rate laws, as we just saw, again, are always determined experimentally. So you will get a bunch of tables. And like I said, it may have multiple entries in there. And again, the numbers may not always be perfectly pretty, which is why you could kind of natural log both sides and do that. It's always defined in terms of the reactants. So there really should be no products in the rate law. And it is not based on the coefficient in the balanced equation. As you can see in this example, for example, the ClO2 has a 2, and then the order here is first order in this case. So they both sort of equally will have an effect right on the rate in this case, as they both are first order. So you can actually play with either one and you'll get sort of the same sort of degree of change in the rate, depending on the concentrations that you change. All right, so I want to try one. The rate equation for the reaction of NO to ozone is the rate is equal to K, NO, and O3. If the rate is 6.6 times 10 to the minus 5 molar second. Look at it. We have the rate law actually given to us, which looks something like this. That means the order with respect to NO is first order, right? The order with respect to O3 is also first order. That means overall this reaction is 1 + 1, which would be second order, right, overall. Now, in this particular case, they pretty much gave us everything that we needed. So we'll rearrange here and solve for K, which would be our rate divided by our NO and our O3. Gives us 6.60 times 10 to the minus 5 molar seconds divided by our 1 times 10 to the minus 6 molar, and our 3 times 10 to the minus 6 molar in this case. Putting that into our calculators here, obviously making sure we use our exponent button. They give us a 2.20 times 10 to the 7. Units here will be molarity on top and bottom cancel. Once again, 1 over molar seconds, which again is the same unit we saw on the previous slide for that problem. And this one is also, again, second order. So you got the same units associated with it. So again, a good way to kind of check yourself as well. I just did the calculation hopefully correctly. I got the right units going on there. Any questions on that one there? All right, so that's a fairly large rate constant, right? Which means probably the reaction is going to occur relatively quick. So why don't we try one here? All right, so using the data from these experiments, we want to calculate the, we want the completed rate law, we want the orders, want the overall order of the reaction, and we want the value of the rate constant. All right, so it takes a few moments there and see what you come up with. Figure out what the rate law is, figure out what the value of K is, and obviously you need to do the orders. Okay, let's take a look and see how you're progressing. So once again here, we pretty much want to find out everything. And this is, again, typical sort of table that you would find. So we'll start with just sort of like the generic sort of rate law for this reaction. The rate would be K, our S2O82 minus to the X, and our I minus there to the Y. So again, the goal here of using the table is to first figure out the orders. And once you have that, then obviously you'll have the completed rate law. You could get to the rate constant at that point. So we're going to do our same approach where we're going to look at the table and again, choose 2 entries where we keep one constant and vary the other. So just looking at it, obviously here, 1 and 2 will keep this guy constant and vary the other. So that's where I'm going to start with. So taking experiments 1 and 2 in this case. Once again, I'm going to actually put experiment 1 up on top for me to give me perhaps a nicer whole number. So I'm going to go with 2.2 times 10 to the minus 4. That will equal our K times 0.08 to the X and 0.034 to the Y. And I'm going to put everything from experiment 2 up on the bottom, or down on the bottom, I guess is a better way to put that. K 0.08 to the X and 0.017 to the Y. Any questions on that so far? Yeah. It really doesn't matter. Typically speaking, most people use X and Y and sort of do it in the order of how it's written in the equation. So kind of make that one the first guy and the second one. Does it really matter? It really doesn't. And some books will even use different letters like M, and it doesn't really matter. Stuff like that. Yeah. Other questions? Okay. So little math here. You signed up for math, not me. All right. So this is 2. And once again, our rate constant should completely cancel, and our X guy here should be the same. So that should completely cancel. That's going to yield us a 2 to the Y in this case, where Y would equal 1. So by using our experiments 1 and 2, we're able to find that the order with respect to I minus here is Y, which is equal to 1. That you do want to keep straight, and sometimes people confuses that or sort of lose track of what is X or Y or whatever letters you're using, which one did they go to, and they sort of, mix them up sometimes. So just make sure you keep track of that one. Obviously it goes with the I minus in this particular case. We're now going to go back to our table, and since we varied I minus the first time, we're going to keep it constant here, and it looks like experiments 2 and 3 will achieve that for us. So experiments 2 and 3 in this case. So I'm going to go with experiment 3 up on top since it looks like it has a little larger of a rate happening there. So we'll go with that. Our K, our 0.16 to the X and 0.017 to the Y. taking everything from experiment 2 up there on the bottom. We'll do that, 0.08 to the x and 0.017 to the y. In this case, we do get a 4. Once again here, this guy's going to cancel. We already calculated that, so really that cancels. You can't leave it off, really. In this case here, that will give us a 2 to the x, I believe. And in this case, our x should equal 2 in this case, yeah. And once again, if you take the natural log of the left divided by the natural log of the right, so basically the natural log of 4 divided by the natural log of 2, you get 2. So again, that's mathematically how you get it if you can't really see it. Or if you kind of put the larger guy up on the bottom or down the bottom, you might get a decimal, so it might be a little harder to sort of visually see that part of it. At this point, we have the orders for this, which means we could write our completed rate law. And our completed rate law in this case would be the rate is equal to K times S2O(A2) minus to the second order and our I minus to the first order. That would mean that overall here, our order would be 2 plus 1, which would be a third order reaction in this case. Any questions so far on that? All right, so now that we have the orders, we have the completed rate law, we can rearrange our rate law to solve for K. And in this case, if we rearrange it and solve for K, K here would equal our rate divided by our S2O(A2) minus, and we need to square it because of what we found there. And this would be I minus. So that's also a question. So obviously, since this is not 1, when we go to solve for K, we do need to make sure that we do square it as well in this particular example. Putting our numbers in, again, you could choose any of these entries. So I'm just going to choose the first one here. And if I do that, I will get, actually, I'll go here. 2.2 times 10 to the minus 4 molar seconds divided by our 0.08 molar squared and our 0.034 molar. And that will get us 2.2 to the minus 4 divided by 0.08 squared and divided by 0.034. Going to give us a 1.01. The units here are, we have molarity on top and bottom, they cancel, going to leave us 1 over molar squared seconds in this case. So that would be the units that we got going on there, which is different units that we saw for a second order, which was 1 over molar second. That one had 2 units, this one's got 3. So sometimes that works out that way. Any questions on that? And obviously you could do to the minus 2 and the minus 1 for the molarity. Any questions on any of those steps? Yeah. You can. So for example, if I chose the second experiment and we put it in there, we would have 1.1 to the minus 4 divided by 0.08 squared. And divided by 0.17 gives me 1.01. And if you did it for the next one, it should be. So because it's a rate constant, it's a constant value for that particular reaction under those conditions. No matter what experiment that you run it under, it should end up the same number. Yeah. Because the order for that guy was second order. So you would need to mathematically, when you go solve for the K, square it. If you happen to have one that was, say, the third order, you would have to cube it, right? And stuff like yeah. That's why we didn't do anything to that one. Yeah. So we just divided it by that, which is basically the same thing, obviously, if you took it to the first order. Other questions? Okay. All right, let's try another one here. Make sure, maybe. I think you got that one next. So we got a few more entries in the table. Same thing. Let's get the rate law. Let's get the orders, the overall order, and then let's also, again, figure out the value of the rate constant. Let's see how we're doing. So in this case, we actually have 4 entries in this table. Like I said, it may be 4, 3, a bunch of them. You may have a ton more. But it doesn't really matter again, whichever ones you kind of choose, as long as again you choose to where you keep one constant, the other one varies. So in this case, our rate law to start with here would look something like the rate is equal to K times our NO2, and I'm going to call that X, and my CO here, I'm going to call Y. Looking at our CO, we could keep our first and second constant here. By the way, we also could keep our second and third, our fourth in this case as well, will be constant. So if we look at experiments 1 and 2 here, I'm going to go with experiment 2 up on top. So it's going to be 0.0082 RK 0.2 to the X and 0.1 to the Y. Putting our 1 up down on the bottom there is 0.0021 RK, our 0.1 to the X and our 0.1 to the Y. Doing a little division here. I'm going to take our 0.0082 divided by 0.0021. That's going to give us something like 3.90476-ish equals our guys this way will cancel. Our guys here should cancel, and that, which is a 1, should give us 2 to the X. Now, at this point, you could call that 4 if you wanted to and just make the math easy for you. If you didn't, you could take the natural log of 2 and take the natural log of this number that you got going on here, and then divide them. So you take the natural log of that number, will give you something like 1.3621968 equals our natural log of 2, which is 0.693 x divided back over. And it'll essentially give you that x is equal to basically 1.97-ish, which is pretty close to 2. And again, if you just rounded it to 4 at that point, you would have got 2 probably a lot quicker. But you can't get that. That it would be the way, obviously, when you don't have pretty numbers sort of coming out in that particular case. Any questions on that? Now, just for reference point here to see if we chose 2 and 4, maybe you did choose 2 and 4. In this case, we will put, looks like 4 up on top, 0.033 equals K, 0.4 to the X, 0.1 to the Y. And in this case, 0.0082 and RK 0.2 to the X and 0.10 to the Y. Once again, here we'll take our 0.033 divided by 0.0082. This one will actually give you 4.024 equals, again here, 2 to the X on this side as those guys cancel out. Once again, you could round the 4, and as you'll see, you'll eventually get to the same x is equal to 2, no matter which one you choose. You obviously could also do 1 and 4 as well, as those guys are the same. So you could choose either one. They all should sort of get you to pretty much the same one. You don't have to do them all. Yeah, they all should be the same, so you could just choose one to do. Any question on that so far? All right, so depending on whichever way you chose there, our order with respect to our NO2 is going to be second order. We're now going to go back to our table and keep NO2 constant. And in this case, there is only one option to do that, which looks like experiment 2 and experiment 3 is the only one that will keep that guy constant. So doing our math here for experiment 2 and 3, I'm going to put experiment, it's pretty close, but we'll go with experiment 3 up on top. Equals our K 0.2 to the X, 0.2 to the Y, 0.0082, which would be our experiment 2, and our K 0.2 and 0.1 in this case. That looks pretty close to 1 to me, yes, and probably not exactly 1, but pretty darn close. That's going to give me K's. They're going to cancel. This is going to cancel in here. That's going to be 2 to the y, which means in this case, y should equal 0 in this case, right? Anything to the 0 order will equal 1. And again, if you didn't do a little bit of rounding there, you would have got 1.0121. You could have took the natural log of it and divided it by the natural log of 2. And you get basically 0.017, which is basically 0 in that sense if you round it to the whole number. All right, so we got some orders working here. So we have our rate. Our rate is equal to K. It was NO2 squared. And in terms of our other guy there, our Y is going to equal 0, which means you really do not need to include it in the rate log because it's going to equal 1. If you do include it in the rate law, do you need to write the 0 on top of it? You do, because if you do not write the 0 and just write, I don't remember what the other thing was, but if you just wrote whatever the other thing was like that, obviously that would imply that it is first order, right? So you do need to make sure you put the 0 there if you do want to include it in there, which is fine. But make sure you put the 0 and don't just leave it blank up there. Otherwise, it's assumed to be 1. And obviously, you don't really need to include it. So at this point, that means our overall order in this case really is going to be 2 plus 0, which is second order reaction. So now we can solve for the value of the rate constant by taking K would be the rate divided by our NO2. And once again, here we do need to make sure we square it because of the second order there. And again, you could choose any of these numbers here. So we'll roll with that. 0.0021, it looks like 0.0021 molar seconds. Divided by 0.1 squared. And then obviously this is 0, so it becomes 1. And that is molarity there. So taking that is 0.0021 divided by 0.1 squared. Going to give us a 0.21 units here. 1 molarity on top and 1 on the bottom there will cancel, giving us 1 over molar seconds, which once again, as we saw a couple of times so far, are the units that we sort of expect to happen for a second order reaction overall for our rate constant. Any questions on that? All right, so let's try another one here to see. Try this one, same thing. Rate law order. Okay, let's take a look. So we're going to do our same approach we've been doing. We're going to start with our rate law here, which is our K NH4 plus to the X, our NO2 minus to the Y there. In this case, we again have 4 sort of entries. So just looking at it, 1 and 2 here will keep our NO2 minus constant. So looking at those first. In this case, I'm going to put number 2 up on top, and that is 32.3, by the way, times 10 to the minus 7, in case you missed it. There is times 10 to the minus 7. Won't make a big difference till the end, but it does make a difference at some point, yeah. So that's going to equal K times R 0.06 to the X, R 0.2 to the Y. Taking our bottom there, 10.8 times 10 to the minus 7, RK 0.02 to the X and 0.2 there to the Y. Doing our math here, gets us basically 2.99, which is basically 3. These guys will cancel. That will also give us a 3 to the X, and those guys will completely cancel, giving us basically our X is equal to 1 in this case. Any questions on that one there? Coming to our next one here, looks like 3 and 4 should do the trick there. 3 and 4 will keep that one constant there, the NH4 plus. it will vary the NO2 minus. So experiments 3 and 4. We can go with experiment 4 up on top. Once again, 21.6 times 10 to the minus 7 equals our K 0.2 to the X, 0.0404 to the Y. Everything in experiment 3 on the bottom, 10.8 times 10 to the minus 7, our K 0.2 and our 0.0202 to the Y. So taking our 21.6 and our 10.8, going to give us a 2 is equal to, these guys should cancel, completely cancel. And it looks like we should get a 2 to the Y in this case. Y will equal 1. So now that we used our table here to figure out our orders, we can see that the rate is equal to K times NH4 plus and NO2 minus. Our overall order here going to be second order by adding those guys together. And now that we have that, we can solve for the value of K. And it is this calculation that if you miss that number there to begin with, this guy, it will make a big difference here because you will not have that number in your calculation. So solving for K here will give us our rate NH4 plus and NO2 minus. So putting in our rate there for the first one, again, I'm making sure I'm keeping that times 10 to the 7 minus 7 divided by our 0.02 molar and our 0.2 molar in this case. Going to give us 10.8 to the minus 7 divided by 0.02 and divided by 0.2. Looks like you got something like 2.7 times 10 to the minus 4 units here. Again, molarity on top and bottom will cancel, giving us our 1 over molar seconds, like we've seen a number of times at this point for our second order reaction. Any questions on any of those steps there? Questions on how to calculate a rate law, the orders, the overall order, the value of the rate constant from experimental information. Again, if it doesn't give you really pretty numbers, again, you can use the natural log of both sides and divide it out. And if it's close to a whole number, you could round. It should be kind of close to the whole number to sort of round, yeah. Any questions on that? Okay, so we're going to talk now about more specific orders of reactions and certain equations that sort of go with it. As we talked about the other day, there's really 3 types of orders of reactions that we very commonly come across, and those are first order, zero order, and second order reactions. And they do have specific sort of formulas that's used for each, for a different type. There's also different graphs that are seen for different types of reactions that we see. So the first type of reaction we're going to talk about is a first order reaction. And a first order reaction really can be achieved in a couple of ways. One way is you just have one reactant and it has an order of 1, right? So if it's the only reactant and it has an order of 1, then the overall reaction would be a first order reaction. You could also have 2 reactants maybe, where one has an order of 1, right? And one has an order of 0, right? That would still give you a first order overall reaction. And in that particular case, as we talked about, pretty much A is the only thing that's affecting the rate, right? B is really not doing anything to affect the rate of that reaction or anything like that. So if we rewrite the rate expression for that and ultimately the rate law for that, which is a first order reaction here, the rate is equal to K times A. And solving for K in just 2 units of K, the very first thing that's really important to know is when you see a rate constant that has this type of units, 1 over seconds, reciprocal seconds, it really doesn't necessarily has to be seconds. It could be any unit of time. So you could have like 1 over minutes, 1 over hours, 1 over days, weeks, years, whatever it may be. Very commonly, though, it will be seconds. As I mentioned before, we don't usually run reactions for years and stuff, you know, so seconds is oftentimes what we deal with, but it doesn't necessarily have to be seconds. So really 1 over some unit of time would indicate to you that it is a first order reaction. And that would tell you that you should use the first order equations we're going to talk about here in just a second when you see that. Like I said earlier, sometimes they will not in blinking lights say this is first order and you should use those equations. They'll give you the rate constant. You'll see the units and you just need to know, oh, those units are associated with a first order reaction. There are 2 types of graphs that we commonly will see for a first order reaction, and really one more than the other. This graph here is the concentration of the reactant over time. And as we would expect, we would see over time, right, a decrease there in the concentration of our reactant as it's going to make products. Pretty much, though, in most kinetics types of experiments and calculations that you do, we're always looking for really the linear relationship that we see. And that's really the second graph here, which is the natural log of A versus time. And the way that we get that is by taking this relationship here and really running the natural log through the whole thing. This is what is sometimes referred to as the integrated rate law. And that is the natural log of A is equal to the natural log of A naught minus KT. The first A here is, you could think of it as your final concentration. Your A with the little circle, which is sometimes referred to as a naught, is the initial concentration. K is our rate constant. And T here is actually time. People always want to throw temperature on that one, but that T is time, lowercase time. Now, that is the integrated rate law. And there's also a half-life equation that goes specifically with first order, which is the half-life is equal to the natural log of 2 divided by the rate constant, which if you take the natural log of 2 is 0.693 divided by the rate constant. The half-life, which is very commonly used in calculations, is the time it takes for half of whatever you start with, basically to go away, right? So if you started with 10, how much time it takes for it to end up with 5, right? And then after that, how much time to end up with 2.5, and after that, I need a calculator, but you keep dividing by 2, right? And how much time it takes for you to do that. And very commonly, both of these equations, the half-life equation and the integrated rate law, is sometimes used together. So sometimes you may be given enough information, but you're kind of missing 2 pieces of information. Like you may be given the half-life, but you're not given the rate constant, but you need the rate constant for the other equation. So sometimes you have to use the half-life equation to get to the rate constant, and then use the rate constant in the integrated rate law to solve for whatever you may be looking for. So very commonly, and we'll see it a lot more common maybe later on when we talk about nuclear chemistry. All radioactive decay follows first order kinetics. So all the radioactive decay and anything that's radioactive that goes through a decay process follows this sort of order of decay that it happens. So how do we get to that equation? Well, if you take the integrated rate law and you do something we all like, which is rearrange it, I suppose, and you take the natural log of A is equal to minus K times T plus the natural log of A naught. So that is just the integrated rate law. This guy here rearranged. And this is rearranged in the form of a straight line. This is y is equal to mx plus b. And that is how we get the graph on the bottom, because on the bottom, on the y is the natural log of A. On the x is time, which means when I solve for the slope of this line, it equals negative of the rate constant. It does not equal the rate constant, it equals negative of the rate constant. That line that is drawn there, is that a positive sloping line or a negative sloping? Negative, which means your rate constant will be what type of number? It should be a positive number, yes, because it's equal to negative of the slope, right? So negative and negative give you a positive number for the rate constant. Keep that in mind when we do the experiment in a week or so, yeah? And then you should get all positive numbers for those things, yes? So you can graphically graph the natural log of your concentration versus time, and it should give you this linear relationship as we see in that graph there of really a negative slope that's happening there. And like I said, graphically, you can figure out the rate constant. You can also obviously use it as an equation here. So there's really a few important things that you need to know for first order reactions that will help you as we go through it here. Definitely the rate constant and the units that are associated with it. You should know both of these graphs and what is being graphed. But again, I will say that this graph here is probably the one most associated when somebody says this is a first order sort of kinetics graph. It will most likely be the one on the right there, which is the linear relationship, which is mostly what we look at. You should also obviously know the integrated rate law, and you should know the half-life equation here. One part of the integrated rate law, which is really important to keep in mind as well, and where people oftentimes will make a mistake, is the back part of it here, where you have the K and the T. The K, which is the rate constant, will have a unit of time, like 1/seconds, right? But it could be like 1/minutes, and the time could be minutes, the time could be seconds, kind of could be days. So those unit of time between those two that I just circled there, you do need to make sure that they are in the same units, whatever unit you want, you have time. But very commonly, those two are in different sort of time units. People forget that and not convert it, and then you're going to be off, obviously, by that factor of the time. Any questions on that there? All right, we will lay it up there.